very much, Leslie, for having me, and thank you all for coming today. The fires seemed like they were a big deal 2 years ago when the Fourmile Canyon fire happened, and they're obviously an even bigger deal now. So what I'm going to talk about today is mostly related to physical hydrology, so sort of the physics of the way water moves through the landscape. I know that you've been thinking a lot about sort of solutes moving through streams, and so if you have any questions about that, I'm happy to answer that. But today I'm going to talk mostly about how the water moves through the landscape and how that's different after a fire. This is actually a picture at night of the Fourmile Canyon fire taken from up on Flagstaff. My apologies to James Taylor for stealing his song lyrics to make my title. And this is some work that I've been doing with Deborah Martin and John Moody, who are also at the USGS. And they've been working on fires for a pretty long time relative to me. They've been working on fires since about 2000, well actually since 1996, since the Buffalo Creek fire. They also worked some on Cerro Grande, Hayman, High Meadow. So they've worked on a lot of the major fires in this area. Okay, so I'm going to start with some what I'll call global pyrogeography. So pyro meaning fire, and geography meaning sort of spaces around the Earth. So where does fire happen? And this map is based on satellite images, so using very large pixels to look at sort of large footprint to look at fire frequency. So how often does fire happen? The sort of black and blues, the cooler colors are very infrequent fires. As we move into greens and reds, and especially in greens and yellows and reds, we get to lots of fires. So those are going to be environments like grasslands and savannas where it burns very frequently, but the ecosystem is very adapted to sort of deal with that. It recovers really fast, and so the impacts are, for the most case, relatively low. But in these darker kind of blue and black areas, typically low frequency, higher impact. So it takes a little bit longer for this system to recover. So the one thing you notice is that wildfire is a global issue. It happens on every continent except Antarctica. And in particular, if you look at the western US, where we are, you see a lot of those blacks and blues that I was talking about. So low frequency, relatively high impacts. I hardly even need this slide given the current situation, but I made this a few weeks ago before kind of the great conflagration in Colorado. But fire is a really big deal in the western United States. The annual firefighting costs on average are about $1 billion. That's just fighting fires. In sort of big years, which it seems like we're in the midst of a pretty big year, that cost can get a little closer to about $2 billion. So it's a pretty serious expense. You can see kind of what associates those expenses. We have a lot of firefighters on the ground. This is actually a picture from Fourmile Canyon. This is you see retardant drops. If any of you looked out your window yesterday, you probably saw a lot of retardant being dropped up on the Flagstaff fire. And so a lot of expenses of driving people around and moving equipment. How much retardant is dropped? Well, in a big season, they've dropped as much as over 400,000 gallons. So that's a lot of retardant being dropped in the landscape. In terms of this problem going away, I think that's pretty unlikely. If you look at the stats, Colorado's 30 largest fires in terms of area all happened after 1996. 80% of those fires, of the largest fires, happened after 2002. So in the last decade, the fires seem to be getting bigger. So if anything, the problem seems to be getting worse, or at least we're getting larger fires, so burning more acreage. So now what I focus on are the hydrologic impacts of fires, and I'm going to talk about that with this kind of idealized conceptual picture of what a forest might look like before and after a fire. So if we look at the before fire picture, what we've got are some conifers. So we have what I'll call a nearly closed canopy forest. What this means is that these trees sort of shield the landscape. They're shielding the soil from getting hit by the rain. And if you look below, you'll see there's this layer of kind of litter and duff, and so those are accumulated twigs and needles that have piled up over the years and decades from those trees. Then there'll be some soil and then some kind of weathered rock underneath it. If we zoom in on this little blue square of what the soil surface looks like, what we'll see is that before the fire, we'll have a couple centimeters of that litter and duff, so pine needles and twigs that are shielding the ground. An organic rich soil, so as all of this stuff decomposes, it mixes in with the soil and kind of opens it up and adds structure that lets the water get in. And then below that, we'll have a mineral soil. Now along comes a giant fire. So the first thing you might imagine is that all of this tree canopy has been burned off. So if you look at this landscape, in a severe fire, that's all gone. So all of that protection for the ground is now gone. If we zoom in at what the soil looks like, we'll see that this litter and duff layer that was also shielding the soil has also been gone. It's been burned into ash. So typically we'll have a couple centimeters of ash that's now been deposited on the soil. That ash typically will last a couple of months until it's blown away or washed away. And then because the winds during the fire, and also because the ash can be mobilized by water in some cases, it'll mix in with the soil in the top couple centimeters. In some cases, we may have areas that are not as severely burned. I've denoted that by there's still some organic material left in that little spot. And then beneath it, we'll probably have soil that's unaffected by the fire. So because the soil is really dry, when you get about 10 or 15 centimeters deep, it's actually not that affected by the fire. So most of the fire effects on soil, in terms of hydrology, are kind of in the top 5 to 10 centimeters. Now, how this changes the hydrology of the landscape are things like interception. So when you think about football, just like a quarterback throws a pass, this is the exact same thing. All of these needles and tree branches and also this litter and duff are intercepting that rain, just like a pass. So they're stopping it. In some cases, they're delaying it. So that, before the fire, a lot of that water from the rain was not even making it to the soil surface. After the fire, obviously, that's all gone. There's also some storage. So the tree branches can hold some of that water. Also, this litter and duff will store some of it and stop it from getting into the soil. There's also a big change in infiltration rates. So infiltration is how easily water makes it across this barrier. So when it falls as rainfall, getting into the soil, that's infiltration. So basically water moving into the soil. Now the reason why that's changed after the fire are a couple of reasons. One, typically ash is really fine grained. So if you pick up ash from your fireplace, you'll notice you can just blow it away. It's really easily mobile. That will actually clog up the soil and stop water from moving in. You'll also get structure loss. So as this organic rich soil is baked, all the cracks and little pathways that you see that water can move in, those have been closed up by the baking from the fire. There's also a big change in roughness. So if you think about water flowing over the surface, it has to move through all that litter and duff, and so it's really slowed down quite a bit. You think about after the fire, this surface is quite a bit smoother than it was before the fire. So we've lost that roughness. So the water, there's going to be more water because less will infiltrate. That means more will run off. It will also be moving faster. These impacts, because we have less infiltration, we have more runoff. We have more water moving over the surface. What that does is cause increased erosion. And also all that extra water will cause flash floods. Some of you may have heard about this in the Hayman fire. So this is an example from the area of the Hayman fire. You can see that this has been burned. A lot of this water has run down through the channel and eroded. It's stripped away sediments from the channel and then deposited them out here. There are also what are called debris flows. So if you make a switch from a mix that's mostly water with some sediment to one that's mostly sediment with some water, that's a transition to what you might call a mudslide or a debris flow, and that's what they get a lot in California. There are also some water quality issues that I'm sure you've been talking about with nitrate, phosphorus, some heavy metals, things like mercury, for example, and also TDS, which are total dissolved solids. I'm not going to talk a lot about those. I'm going to focus more on increased runoff. So an example would be oh, sorry, go ahead.
It's okay. So what I had heard a few times during the wet season, right after Fourmile Canyon fire and the predicting flooding, that the soil had become hydrophobic.
Sure.
So is that just an easy way of saying the infiltration rates have decreased, or is it really hydrophobic?
Yeah, so they're actually linked. What the hydrophobicity refers to is that there are certain organic compounds that can be deposited on soil particles themselves that actually stop them from being wetted up. So it's sort of like if you've ever watered like a house plant when it's really dry, have you ever noticed that sometimes the water doesn't go in? That's because there are actually organic compounds that actually stop the material from being wetted. And so typically the fire will remobilize those and then deposit them in a layer either very near the surface or at depth. And so that actually stops infiltration quite a bit. So beyond the things that I talked about, like clogging, for example, there is hydrophobicity also. And that was present in some cases in the Fourmile Canyon fire. So they're a little bit different. It's almost like as if you melted a candle on the surface of the soil. It can be that hydrophobic. You can put a drop of water and it will sit there for half an hour and not go in. Good question.
And those are organic?
Yeah, they're organic materials. And I can talk more about that if you have questions about hydrophobicity.
That could be a lunchtime.
Sure. Okay, so when we start talking about increased erosion and more runoff, a lot of times you'll get a lot of sediment and ash, and so we'll get things like fish mortality. We'll get a lot of sediment in the headwaters. This is trucks from Denver Water that are trucking sediment out of headwater catchments so it doesn't make it into reservoirs. In some cases you'll get a lot of ash and fine sediment moving into headwater streams and clogging them. In some cases here you can see this is one of these, like a tributary like this that's going into Cheeseman. That's kind of sediment full. So there can be a lot of water resources impacts to this. And so you see people doing things like reseeding and trucking out sediment. Another example, kind of more on the debris flow end, would be the station fire. This was in 2009 outside of LA. This is work done by some folks at the USGS. They work more in an environment where there's debris flow, so more like mudslides, and you can see here's a house that's been overwhelmed by one of these. They put out instruments to try to monitor and measure these debris flows to do better predictions of runout and things like that, and this stuff just gets completely destroyed by one of these, and so it's definitely a really hard thing to monitor. If you've ever read John McPhee's book, Control of Nature, he talks about debris flow basins, so there's a lot of these. This is a person for scale from about here to here. So they build these giant basins that basically catch all of this mudslide debris from getting to houses downstream, and then they clear it out with dump trucks, and then they kind of keep that cycle going to protect. So you can see there's a lot of impacts from these fires. So by getting less infiltration and more runoff, you can really generate a lot of natural hazards.
Is the station fire the one that was up in like the San Gabriel Mountains?
Yep.
That was
Yep.
so big?
Yeah, it was all in the San Gabriel. That was a very big fire. So I'm going to talk mostly about the Fourmile Canyon fire, which is where most of my work has been done since being in Boulder. It's about 2,500 hectares, and originally when I came here, I was actually supposed to work on California fires, but because my office is here, this fire is here.
Proximity.
Yeah, proximity means that you can do a lot more with a lot less money-wise, and so you end up trying to monitor a place that's close. This is kind of a very unusual opportunity. And I know that you've been up here, so you went up Gold Run. I'm working at the top of Sugarloaf, so right on the very edge of the fire. And there were a couple of reasons for that. One is that Deborah Martin, who was one of my colleagues, her house was actually burned in the fire, and the private property that she had gave us very quick access to kind of set up a research site. One, there are a number of houses along Fourmile Creek itself. It's also a tributary to Boulder Creek, and so when I talked about things like flash floods, one of the concerns was, will a huge thunderstorm here generate a flash flood that runs down and goes right through the city of Boulder? So that was definitely one of the things that we and a lot of other people were very concerned about. So I'll talk just a little bit about how the fire started. You're probably a little more familiar with some of these terms now that you've heard them in the news lately. So from August 1st to the end of the fire, Boulder got about 32 millimeters of precip. That's about half of what they would normally get during that time. The Front Range foothills, where this fire actually started, got about a quarter to about 50%. So really dry conditions, not quite on par with what we had as before yesterday, but pretty close. And on the day of the fire, really low relative humidity. So when you hear talk about red flag, that's typically going to be really low relative humidities and really high wind speeds. And that's a problem because it drives rapid fire growth. So Smokey the Bear would say very high. This probably would be extreme on the day that this happened. And what this fire growth does is, in the Fourmile case, you have a fire that initiates down in the canyon at about 10 a.m. In 2 hours, it burns that much area. So you get a sense of the speed of the spread and why it destroyed so many homes, is it spread so fast that you just can't bring resources, and it's too dangerous to put firefighters into a situation like that. So at 2300 hours, this is 13 hours after the start of the fire, the green area has burned. So basically most of the area of the Fourmile Canyon fire burned in the first 13 hours. So you get a sense of the speed that these things can move. You probably saw that in the news with the Waldo Canyon fire, how fast it can change. It's really unpredictable and very dangerous. And then it slows down a little bit. So 3 hours after that, you kind of add in the yellow areas. Then on the 8th, it fills in a little bit to the east, over towards Boulder Heights. And the 9th, you add a little bit. 10th, it's basically contained. Doesn't spread much more, and that's kind of the final fire line. In terms of fighting the fire, it was contained on the 13th. The suppression cost was about $10 million. Peak personnel, in terms of people working on it, was about 1,000. It seems like a lot, but it's about half as many at the peak as are working on High Park, the recent one near Fort Collins. So the aftermath, this, I had noticed I had the asterisk now, was the costliest fire in Colorado history. that will probably easily be surpassed by both High Park and Waldo Canyon. I mean, that's unbelievable. I would have never have thought that that could have happened in the last couple of years. There were over, so there were about over 200 million in losses. There are still about 300 homes within the burn perimeter, and so that sort of gets you thinking about these post-fire hazards that I've been talking about. You'll notice like the house here and house here. Now these are up on the ridge. They're not as vulnerable as the houses that are down actually along Fourmile Creek, and you probably saw some of those yesterday. So we're trying to figure out what happens with the hydrology, and to do that we put in a variety of instruments to measure that. We want to know how much rain falls, so we'll put in tipping bucket rain gauges. So how these work is that you have two little buckets and the rain falls and then it tips, and so each tip is a known volume, and so you can compute rates for how frequently it tips. We also have visual gauges, so that's kind of old school farmer style. You just go out and you read it yourself every day. And that's a good check on these automated gauges. To measure the runoff, how much flows over the landscape, we have some small areas that are instrumented with flumes. And so we know by how high it is in the flume, how much discharge, how much volume per second is flowing through there. So we have ultrasonic sensors that send out a little pulse and tell us how high the water is. And those are buried in these white canisters. We also have a weather station that measures things like air temperature, relative humidity, and wind speed so that we can figure out evaporation, how much water is leaving the soil and going into the atmosphere. We also have what are called infiltrometers that I'll explain a little more later. So that's trying to measure that infiltration, how much water is going into the ground. And I'll describe that a little more in a bit. We have sensors that measure soil water content. So that's how moist the soil is, and those we bury in the ground and calibrate, and so they measure an electrical response. We have what are called tensiometers that measure the pressure in the soil. They're called a tensiometer because it's under tension. It's actually less than atmospheric pressure. It's below zero. The water is actually like sucked to the soil. We also have samples that, these are samplers that pull water out of the soil. So if I put a bottle on a vacuum, I can actually suck some of the water out of the soil and look at things like ammonium and nitrate and phosphorus. And because it snows here, I had a snow depth sensor that measures how thick the snow is over the ground. And so the study area, Fourmile Creek is down here. This is a map. This dark dashed black line marks the burned and unburned line. That's kind of the fire perimeter. And so Sugarloaf, if you know Sugarloaf Mountain, it's right over here. And so I have a number of sites. There's an unburned north-facing site. So the reason why these are different is because there's very different vegetation on different aspects. So north-facing slopes tend to be a lot cooler and wetter, and so you have more trees and they're more closely spaced. South-facing, you get more grasses and sparsely spaced trees, and they're actually totally different tree species. So I instrumented north-facing sites, both burned, the black stars, and unburned, which is the white star, and then also south-facing sites. So the black stars are the burned sites, and the white stars are the unburned sites. You'll notice there's a couple of unburned sites in the fire. That's because there are actually pockets of unburned areas within the fire itself. And so if you look at these, this is a north-facing slope. It's actually covered in snow, but you get a sense that the trees are pretty closely spaced versus a south-facing burned site where they're pretty sparse. And then on the north-facing here, you look at the unburned, you can see there's that litter and duff layer that I was talking about, all those piled up needles and twigs that are shielding the soil, and then all the trees that provide that interception. On the south, that's totally not the case. You have sparsely spaced trees with grass that has no litter and duff, and there's very little interception because the trees are spaced so far apart. So we were interested, because Fourmile Canyon has a lot of north and south facing aspects, how differently those might respond. It also matters, It also matters for snow. So it turns out that north-facing slopes, because they're colder, especially in the winter, that aspect difference is exaggerated. They get a lot less sun. So the snow hangs out longer and actually builds a snowpack that melts out in the spring. Whereas the south, it gets a lot more sun, and so the snow doesn't hang around. It falls basically all winter and spring, and it melts within a couple days. So you have a very big difference that affects the type of recovery that you were talking about for vegetation.
Did we see any increased avalanches? Because there are some steep slopes in that area.
Up there, especially for that year, there's so little snowpack that you don't really get enough to generate avalanche instability. You're talking, like the peak sort of snowpack was like, maybe 18 or 20 inches. So even though the slopes are very steep, in a lot of places, 20, 30, even more, even steeper degrees, you don't really get a lot of avalanche.
Even though it was a big snow year.
Yeah, I mean, maybe if they had a huge snow year, it could be a problem, but in this case, it doesn't seem to be. So I talked about, there's differences in vegetation. So if you look at unburned, north-facing has this dense canopy forest, whereas south-facing has sparse forest with grasses. And so that it's a very big difference between south and north after they burn. So there's also what I'll call the 4 seasons of Fourmile. So in the fall, this was right after the fire, there's this layer of ash. We get frontal rain. So if you're familiar with kind of those fall storms where it's a really long storm, hours and hours or all day, but it doesn't rain very hard. And then in the winter, we tend to get snow and the soil is actually frozen. So the water doesn't really move under the ground at all. In the spring, we switch to a mix of snow that melts pretty quickly and then back to this frontal rain. So not very hard, but really long duration. Then in the summer is kind of the big money season. It's short storms that it just pours, and that's really when we get things like flash floods here. And you can even see a little bit of erosion on this slope. So our general research approach was to look at kind of scales that build up from small to really big. We mostly use field and laboratory measurements combined with some numerical models that tell us how the water moves through the landscape. And so talk about things like the plot scale being a couple meters squared, so kind of like I could wrap my arms around it. And then we move to what I'll call the catchment scale, which would be like a few thousand meters, and those are kind of some of our bigger sites, all the way up to the watershed scale, so like a couple kilometers squared, and you can see how these scales kind of fit in with each other. So the idea is that you try to figure out what's going on a small patch, and then you try to kind of compare that, well, does this small patch work throughout this entire section? And then we say, well, do these same kind of physical models and processes apply at really big scale so that we can predict and tell people when there's going to be a flash flood? So I'll start with talking about the plot scale. And I'll talk about one of the things that we measured is what's called soil water content. This is a really kind of important thing for subsurface hydrology. And so if you think about just like a dry soil, like if I take a handful of dry soil, and you looked at it under a microscope, what you would see are solid grains, so things like sand and silt and clay-sized particles all packed together. And if I totally dried it out in an oven, there'd be no water in there, and so all of the spaces in between those soil grains would just be pores or just airspace. Now if I took that soil and I totally saturated it, I wetted it up until it couldn't hold any more water, it would be totally filled and the porosity would be sort of totally water filled. So all of these little pore spaces are completely filled with water. So that's how it might be after a really huge storm. It's just totally water filled. It can't take in any more water at all. Now if I let it dry out a little bit, what you'll get are these pore spaces would be kind of half air and half water. So when we measure soil water content, we're trying to measure somewhere in this range, so kind of between dry to water filled. And really it's a volume. It's a volume of water over a total volume. So it's how much of this box, or actually really this box, is filled with water. How much water is contained in that box, and that tells us how moist the soil is. I would call it saturated when it's totally filled, and I would call this unsaturated. And this would be oven dry, basically.
Okay. Why are you more interested in unsaturated soil?
So one, it sort of tells you how much space you have for rain. So when I talk about that water, that infiltrating water, it tells me how much space do I have until it's saturated. Because if it's saturated, it can't really hold much more, and then it's going to flood. And it also provides water for plants. So if it's super dry after the fire, or if you've lost a lot of storage, you may not have a lot of water to get plants established, for example. So we're interested in kind of how wet it is. This amount of water also impacts things like hydrophobicity, which you asked about. So wetter soils are not as hydrophobic as drier soils. And so if it tends to be drier after the fire, it may tend to be more hydrophobic, and you might get less infiltration and therefore more runoff. Okay. The other thing that we measure is what's called matric potential, which is actually, this is a relatively complicated concept. And so when I talk about those pore spaces, if we think about those spaces as being like straws, like when you go to McDonald's and you get like a soda straw versus the coffee straw, if we think about a whole bunch of straws of different sizes, that's how we can think about these pores. And it turns out that those straws will empty and fill at different pressures. So when it's really dry, the pressure is really negative. Only the smallest straws will be filled because they can only sort of hold in that much. They can only sort of hold water at these really low pressures. Now when I fill it up, that means like the big straws are filled. So when it's really wet, all of the straws are filled. And when it's really dry, only the tiniest pores, the tiniest straws are going to be filled. And really this tells you how easily water moves through the soil or how easily water is pulled out by plants. Sort of like, if you go and you get a shake at a place, if they gave you one of those coffee straws, there is no way that you would ever be able to pull that shake out. But if they gave you a straw that was this big, you could get as much shake as you want. Same kind of idea with either moving water through the soil or with a plant. This is kind of the energy that it takes to either get things out or move it through in a simplified sense. So that's why we're measuring this matric potential.
So what sort of number is that?
Usually, you can think of it as a pressure, but we usually talk about it in an equivalent height of water, so centimeters of water, or you could think about it in inches if you didn't want to use metric units. So we think about it as a height, and so it's strange that it's actually a tension. It's negative because the soil is holding onto that water. The straws are holding onto that water and they don't want to let it go. And so the big straws let go of their water really easily, and the smallest straws hold it really tight. So it's a really large negative number is when it's really dry. So I talked about these infiltrometers, and so this is kind of a cartoon diagram of what that is. We have a rain gauge that measures how much rain falls from the sky. Then we have a closed plot, so we've sealed this off so that no water can get in from upslope or from the sides. And then we have a pipe that's concreted into the ground and it runs the water. All the water that's collected here from the rain comes through this pipe and is measured in a second rain gauge that's a runoff gauge. So then we can know the difference. If we know how much falls and how much runs off, the difference is just the infiltration, how much went into the ground. So we're trying to measure how much goes into the ground as a function of time so that we can build better models and understand how much runoff is there going to be, how much runoff will contribute to a flash flood, for example. And we have water content sensors that tell us how wet the soil is when that happens. And so here's a photograph of these installed in one of the burned areas. And so they're a little hard to see because we paint them black to camouflage them so that for vandalism and things like that. But I've circled them. Yellow dashed is a rain gauge. So here's a rain gauge mounted on a post. And it's tensioned with wires to hold it steady during the winds from thunderstorms. There's a runoff gauge. So here's that little plot that I was talking about. It's about this big. I could pretty much wrap my arms around it. And then that water is routed into a runoff gauge. And so we can sort of normalize these two areas to get sort of millimeters per hour, like a rate of rain falling and then a rate of runoff. So I could say 40% of the rainfall runs off, or 10%, or 90% as a function of time. And then we have this is a logger that houses a little computer that stores all of those automated water content values. And the sensors themselves are buried in a trench that's below the ground, so you can't really see it. So we have a couple of these installed. We had some on the Sugarloaf site that I'm talking about, and we also had some on the other side over kind of by Long Gulch, if you know where that is. So where you made that turn to go up Gold Run, if you keep going up that road to the very edge of where it's burned, we have another site that's back there. That's actually regrown so much that we abandoned it this year because we didn't think anything was going to happen, but we're still monitoring the Sugarloaf site. And so these difference infiltrometers produce this kind of data. So if I plot rainfall intensity, so how hard it rains, against runoff, how much comes off in millimeters per hour, so a rate that's normalized by the areas of the rain gauge and then the size of that plot that's collecting it, you basically get kind of different storms. So I talked about kind of those spring storms, these frontal storms that are low rates. It doesn't rain very hard, but it rains for a really long time. You can see this is like 7 hours long of rain. And the blue line is the rain, and then the red line is the runoff. And so you can see that after the soil gets really wet, like it can't hold any more water, almost all, thinking about normalized by area, almost all of the rain is running off. So basically the soil is totally filled. Now if we compare this to a convective storm, this one's in July, we look at a similar graph, and notice these are on different scales. So this is low intensity, so like 10 millimeters per hour, versus, and so think about there's 25 millimeters per inch. So that's pretty low. Versus something like this, where it's 45 millimeters an hour, you can see, well, it doesn't last very long. Here these little cells are only 10 or 20 minutes long. So here we have a big spike of rain and there's no runoff at all. Here we have another big spike of rain but there's not as much runoff. But there's a lot more runoff than there is here, but in terms of the relative fraction of rainfall. So we're trying to understand the difference between these storms and which storms will generate floods and which ones won't. It's all infiltrating, exactly. Okay. So in that sense, what that instrument is telling us is that every drop, basically is going into the ground. So we're getting no runoff at all. So exactly, all infiltrating. And that's because dry soils, I talked about that the matric potential being negative, dry soils actually pull more water in. So if I would look at infiltration, I, as a rate like millimeters per hour, this might be hard to see from back there, and if I had time, like during a storm going this way, usually what you'll see is that infiltration rate will drop and then level off. And so like for this storm in July, what you probably have is you're starting out somewhere up here, and your rainfall rate is like here. So you're raining, but it's all going in the ground. And then when we get further out, suddenly our runoff is basically the difference between those two for a constant rainfall rate, although obviously the rainfall rate is not constant. So that's kind of what we're getting at, is that over time, how much water that soil can pull in based on how dry it is goes down.
Thank you.
Sure. So that's not the pointer. Where's that, the remote? There we go. So another way to think about, that we think about this, are these infiltration models where we try to figure out the physics of how that water moves in the ground, and so then we take that infiltrometer data and we simulate it with a model, and we try to fit the model, which is the green line, to our observations from the infiltrometer, which is the red line. So and here's the rainfall signal. So we're trying to better understand using models and then try to use those models to predict at big scales when are there going to be floods. So that's really kind of the ultimate goals. That's why we're out there collecting all this data.
And real quick, can I ask, are we looking at data from the site that was burned or unburned? Or
this is burned. This is from the Sugarloaf site at Fourmile Canyon from last summer.
On the burn side?
Yeah, on the burn side.
Okay.
Sorry, I should have made that clear. And so when I talk about the differences of like how runoff is generated, so what causes runoff, there's usually two kind of ways of thinking about this. One is what's called saturation excess, meaning the soil gets saturated. It's totally filled up and it can't take in any more water. And that's common during kind of low intensity but long duration storms. So it's not raining very hard, but it rains for a really long time. And so if you think about the soil as being like a sponge, usually what that means is that it's coming in and all of that rain, like we saw, is going into the ground. And then over time, eventually the rain keeps falling and then it fills up the sponge, can't take any more water, and then we get runoff. Kind of the opposite model of this is what's called infiltration excess, meaning there's more rain falling than can infiltrate. So we have an excess amount. This is going to be like high intensity, short duration, so like a convective summer thunderstorm. So you can see we've got a lot more raindrops here than we do over here, and it's just going to rain way harder than it can go in. So we get kind of immediate runoff generation. But we get a little bit that goes in. There's some amount that does go in, and so that amount is going to move down over time. And this is going to be different in what we see. So if you think about a threshold, like what causes the runoff, saturation excess, it's going to be total rainfall. How much rain does it take to fill up our sponge? If we move to something like infiltration excess, so a thunderstorm, it's going to be a threshold that's a rate. How hard does it have to rain to not all go in? So we can look at, if I go back, and I have to go back quite a ways, but if I look at these two storms, you might guess that this low intensity, long duration storm where at some point all of the water basically runs off might be the sponge filling up. That might be saturation excess. Whereas this storm, where it's raining really hard, it's just pouring, might be infiltration excess. It's raining so hard that it just can't all go in. And so trying to understand these different processes to better predict when there will be floods. Another way of looking at this is what's called hydrogeophysics. So it's basically using physical methods to look underground at the way water moves. And we've been working with what's called electrical resistance tomography, which is kind of a long term. But think of it as like a CAT scan or an MRI if you've been to the doctor, but like of the ground rather than of your knee or your brain. So what we're doing is we're putting in all of these white poles, our little electrodes. And what we'll do is inject a current and then monitor a voltage. So you're basically making a little circuit out of the ground in a whole bunch of different places. So we make little circuits out of all of these different poles in different sequences. And using all of that, we can sort of invert it and get like an image of what the ground looks like. And the reason why that works is because electrical conductivity depends on that water content that I was talking about. So wetter soil conducts electricity better. Dry soil is a really poor conductor. So we can generate images of burned and unburned soil. So if you want really kind of tight spacing, a really detailed image that doesn't go very deep, you put them really close. So in this case, they're 1/4 of a meter. But you could make them a meter apart or 10 meters apart. You'll get a coarser image, but it'll go much deeper in the soil.
And how deep does the pole go typically?
These are pretty shallow. They're probably like that deep. So we were installing them basically with a giant drill bit that we would drill into the ground.
Like 10 centimeters or like?
Yeah, like probably 10 or 15 centimeters. And then what we would do is squirt. You've ever been to the doctor and they put that electrically conductive gel on you to do tests, like an ultrasound or something? That's what we use. So you put that in the hole so that you get a good contact between the soil and this electrode. And then we have an instrument, this white box, that sticks in the current and monitors the voltage. And so we were doing this in both burned and unburned sites by sprinkling on it. So I backpacked in a bunch of big jugs of water, and then we used sprayers to wet the soil at a controlled rate. And I tried to get natural rain a couple times, and mostly what I got was hailed on, which is interesting. Doesn't quite work when you get hailed on. But so that's another way to sort of see the way the water moves and see into the soil.
So I noticed those are like really long arrays and they're on a slope, so were you
Sure.
expecting to see a difference, like at the top and the bottom?
So actually these are installed, the slope runs this way, and these are actually installed, the area is flatter than it looks, and so they're kind of installed like on kind of the same level, but a slight slope downward. So we were trying to sprinkle on it in a way that it wouldn't move a lot downslope.
So I'm just wondering why that array is so long? Like, do you just want one sample?
Well, so the reason why is that if you did it truly in 3 dimensions, this is a good question, you would do it as like a box. We're actually doing 3 long lines. So really what we're doing is iterating along these lines. So you stamp out like a template, so like 2 current electrodes, 2 potential electrodes, and you just march along. And then you move them a little apart and you march along.
Oh.
You move them a little further and you march along, and as you move them further apart, you get deeper. And so really what we're doing is we're using the length to get a little bit deeper. But because we want to get tight spacing, we have to have close electrodes. So we're trying to sort of get a tight, sort of like really detailed map, but also get some depth out of it. So that's why they're aligned so long. Good questions. You've talked some about nutrients in the creek. We were also looking at nutrient movement below the ground. This was working with Eve Hinckley, who works at NEON, the National Ecological Observatory Network, which is here in Boulder. And so where I had these water content sensors, she also put lysimeters, which we put a vacuum on a bottle and it pulls water out of the soil over a day. And then we look at things like nitrate and ammonium of the water that's coming out of so this is water that's moving into the ground and from the subsurface. So it's sort of like, what you eventually see in the creek is kind of like what we're capturing up on the hill slope. But it takes a long time to get from the soil way up here on Sugarloaf all the way down into the creek, unless it's washed over the flow. But in the subsurface, it takes a pretty long time. So then we also took some measurements at the catchment scale, so this bigger scale, and those are these flumes that measure runoff. So instead of looking at these little infiltrometers, which are like this big, now we're talking about measuring something that goes all the way up to this ridge, so a couple thousand square meters. The water runs off and runs through this little flume, and then based on the height, we know how much is coming off per time. So we have a couple of these. These are all in the burned area on the north facing slope. They work well most of the time, except when you get a really big storm. And you get a lot of sediment. And then I'm out there all day with an army shovel digging them out. So you can see there's, rocks that have been jammed in there. There's some straw that they dropped to cover the hill slopes to try to prevent from erosion. So you sort of get a sense of, if you want to get these little itty-bitty storms, like right at the thresholds of what generates runoff, then sometimes you don't capture the really big ones. A lot of times the big ones take out your instrumentation. So you can see there's quite a bit of clogging by debris for some of the bigger storms. And I had this, what I thought was a really great idea of putting out these little 5-gallon buckets below there to catch all the sediment. If it even sprinkled, these were totally full. And sometimes the buckets were like 40 or 50 yards down the slope. Like they would just be tipped over and rolled down. So burned areas are a pretty challenging environment, and there was a lot more sediment coming off of there than I ever imagined there would be. So we got some data out of these flumes. So just like you saw with those little infiltrometers, we're getting similar data but at a much bigger scale. So if we normalize by the size, we can look at kind of how much, well in this case we're looking at not normalizing by size, but we could do that. But this is just rainfall intensity, and then this is runoff in liters per second. So this is that 10 July storm where, as you pointed out, it all goes in initially, just like we saw in those other ones. But here we get quite a big runoff event, so 4 liters per second. And then that's just a little flume, and then this sort of little flume is embedded in an even bigger flume. So at a bigger scale, you can see that we get a lot. This is different scales. This is intensity, so how hard it rains, and this is runoff, so liters per second that's coming out of the flume. So kind of as we build up in scales, we try to understand what goes on at these different scales to predict at kind of watershed type sizes. So that's kind of the ultimate goal. So last summer we collected a lot of data, and we're still collecting some more data at these smaller scales to work at what goes on at the watershed scale, and that's kind of where we're, I wouldn't say stuck, but progressing. And what happens at the watershed scale from these burns is pretty impressive. So in the summer of 2011, last summer, this is a picture that I took in the 7th of July. Only 20 millimeters of rain, so less than an inch, but pretty high rates. So 70 millimeters an hour is raining pretty darn hard. This is a picture of Fourmile Creek itself. You can see it's totally full of ash. This is one of the first big events after the fire. And then the 13th was even worse. So here you can see this is a car that's been buried in Fourmile Creek Canyon by one of these flash floods. This was down near Emerson Gulch. I don't know if you guys went by that yesterday. So it's, where their car was parked is pretty interesting. I'm not sure that I would have parked my car there. But yeah, there weren't like 20 of these cars. There was only a little bit of damage. But there are some pretty impressive YouTube videos of the flash floods from, especially this event, which actually was my birthday. It was kind of crazy to have that storm on your birthday. But so then also in, this is Fourmile Creek. This is kind of near the other outlet, the other side of Emerson Gulch. And they put in what they call trash tracks, which are these big metal barriers to stop debris from washing over the road. And remember I talked about, one of the worries was flood hazard in Boulder itself, because Fourmile Creek is a tributary to Boulder Creek. This is the flood wall, right? If you know where this is right, that walk under Broadway. So this is not that far from the top. This is the 13th of July. So, this is, in terms of thunderstorms, this is kind of garden variety. Like you get, easily one of these every year. So, in terms of having a really big event last year, they pretty much dodged a bullet. I think they got pretty lucky. And hopefully a lot of the hazard has passed this year, but we're still kind of monitoring it to try to capture if there are any big events or if these thresholds have changed. So how long does it take before this area is not vulnerable to things like flash floods anymore? So yeah, that was, these were kind of two of the really big events last summer. So, and part of that is, we sought out a severely burned fire. Just because you do get the biggest signal, and those are sort of the most hazardous conditions. So we really sought out an area that was very, severely burned, and they have classifications for these things. So yeah, it was definitely a really good opportunity for me to study a fire that had, a lot of potential human impact, but also scientifically had steep slopes, a big difference in vegetation, and a rainfall regime, thunderstorms, that is pretty conducive to flooding under the right circumstances. So yeah, kind of, as I've kind of gotten at, what we're trying to do is connect these measurements and models at these nested scales and try to really build better warning systems that we can kind of pass on as tools. And also using models to sort of fill in the blanks. When you take these measurements, you're never going to capture every rainstorm or every little threshold. And so you can try to use models to kind of fill in a what-if sense. Like, well, what if it had rained twice as hard, or 4 times as hard, or twice as long? And so you kind of, work your way along and really try to fill in what's going on. And better understand things like runoff, natural hazards, how much sediment comes off, and what are these nutrient loads.
Is that picture water? Or?
This is water. This was
Okay,
right
I
after
can
the
tell.
fire on the 22nd of October. The fire was sort of put out on September 13th, and we got in there immediately and put in instrumentation. And so we caught 2 little storms, one on the 12th and one on the 22nd, when there was still ash, which soaks up some of the water. And the ash was stripped off by high winds in the winter. in this site and washed off by some of the rain. And so in this case, you can see this is just a little bit of runoff being generated right as the ash kind of fills up. So we were actually out there when it was raining, kind of watching it. Not intentionally, we just actually happened to be there when the storm came through. So I'd like to thank the Mendenhall Postdoctoral Fellowship Program, which provided the funding for me for the last 2 years to be here and work on this, and conversations with a lot of people that were very helpful, and also some field assistance from a couple folks. So that's great. If you want to talk about vegetation recovery, I have some interesting pictures, but thank you very much.